basophils. Basophils release histamine and heparin. Ooh. That's your allergic reaction. Histamine is important because what it does, it's part of the hypersensitivity reaction. When we get, hay fever coming in, and then, we release histamine, which increases vascular permeability. And it also contracts smooth muscle, but the increased vascular permeability tells you in that area where that thing is, that nose is running. You got those vascular things, ditches, everything's flooded with fluid. That's the histamine response. And then heparin is an anticoagulant and helps the blood not from clumping together and coagulating out. So it increases the blood flow. Which is also good because you want to, if you have a real good reaction, that's good because you want to flush the stuff out. The problem is we often get a little overreacted to this stuff. And then we suffer. The eosinophils are interesting because what they do is they phagocytize, they eat excess histamine to limit an allergic reaction. So that's nice. They also eat, they also eat parasitic worms. So those are the three granulocytes. Not too complex, right? You can handle that. And then we get to the agranulocytes. The first one I talk about is the lymphocyte. They're very small in the bloodstream, but they get large when they go to the lymphoid organ. And most of them live in the lymphoid organs. Those lymphocytes are your B cells and your T cells, and we'll talk extensively about them on Monday. They're really cool. I love them. Well, we all love them. That's why we're here. The last one that I find here is a monocyte. In the bloodstream they're called monocytes. Outside the bloodstream they're called macrophages. So they're big eaters. Macrophage is a big eater. They eat a lot of stuff. And they eat cells that are infected, but then they don't die. They take the part of the cell of the pathogens that is that active site that that flag, and stick out the flag on their outside and say, hey, I got one. And show them to other cells, and then they recognize them. These are then the T cells and the B cells. They recognize them later, those pathogens, and then they can proliferate and make more of themselves and then shoot them down directly. Or produce these antibodies that go to that direct pathogens and glue that together and make it visible for other T cells to shoot down. So that's kind of cool, huh? Or are you completely overwhelmed with that? The yellow thing here is a T cell eating something. A cancer cell, attacking a cancer cell. So that's pretty neat. This here is a monocyte throwing lassos around E. coli and taking them in to ingest them. Eat them up. It's like a Wild West over here. When a cell, a white blood cell, a macrophage or a monocyte does that, eats up a pathogen and then presents the active piece. We call that an antigen-presenting cell. Down here. Platelets is the next thing, and platelets are very interesting. They help us in making a blood clot. Basically fragments. The bone marrow has cells called megakaryocytes. I should have italicized that. And they release platelets into the bloodstream, which live for about 5 to 10 days, and then the spleen destroys them after that. And their main importance is in blood clotting. They make a plug. So let's go briefly through the blood clotting. When we injure a blood vessel, that is a life-threatening event because we don't want to have blood loss. So after injuring a blood vessel, the first thing we need to do is stop, arrest the bleeding. Stop the bleeding. That's called that hemostasis. And we do that by vasoconstriction. Remember that term, vasoconstriction? Narrowing the cell, the blood vessel that brings the blood to that area. So that's the first thing we can do. Shunt that blood off so it doesn't spurt out of the blood vessel. And then after that, we make a platelet plug. So a platelet plug is platelets, which we also call thrombocytes, so I want to make sure you get that term a couple times. Thrombocytes are deposited on the injured vessel wall. There's multiple things that cause that. Part of it is an exposure of calcium, so you guys get into that later, or read in the book. There's already pretty good detail in the book you have. So, but this deposit of platelets activates those platelets and makes them sticky. And that way they can stick to one another and make a plug, make a bigger piece. And I always think of making a snowball and then throw it. We call that technically aggregation. That those platelets come together. And then after that we need to coagulate blood to then make a blood clot. This process is very, very delicate and has many steps. So this is a cascade, meaning many steps involved, many reactions. Because if we do this when we shouldn't do this, when it's not necessary, this can occlude the blood vessel and give us a heart attack. Make a thrombus. When this coagulated blood that's created on the wall breaks off, we can have fragments, we call them embolus. Embolus is that one fragment, move through the bloodstream, and that can clog a blood vessel, causing a stroke. So those are important pieces to understand. So the last step is when we make a soluble fiber, that fibrinogen, which is soluble, and we make it into an insoluble fiber, and we call that fibrin. And that fibrin then clings to the injured wall, trapping a whole bunch of stuff, red blood cells and platelets mainly, and looks something like this over here. And then, of course, the blood vessel will heal slowly, and once that is healed, we need to get rid of that thing, that clot. And the process, we need to actually dissolve it, because we just don't want to just get rid of it. That way we create the strokes. So we have an enzyme called plasmin, and that dissolves that clot, and dissolving that clot is called fibrinolysis. There's the word lysis again, breaking down, killing. So we break down that fibrin mesh verb, and that dissolves the clot. Well, let's go to plasma. Well, plasma. If we take a vial of blood and we put it in a centrifuge, which means it's something that spins really fast and goes in an angle, the harder elements will move all to the bottom. The non-cellular components, that's the plasma. Now if we take, did I put that? Yeah, if we take essentially the extracellular matrix is the plasma. The ground substance is plasma without fibers. And that would be called serum. 90% of plasma is water, 10% is dissolved substances. Most of them are proteins. So about 7% therefore is about protein, about 2% or 20% of the 10, we'll make it more complicated, is low molecular weight stuff, which is nutrients, vitamins, waste products, hormones. And then we also have about 1%, and that's electrolytes. And remember, that's the salts that are dissolved. That can create that electrical current. Right? Now you look at the proteins, what functions do we have? I like this here. They do, inside the blood, they do a bunch of functions. One of them is to transport lipids through the vessels. Cholesterol stuff. We'll get to that. Then they help in blood clotting. We just did that. The fibrinogen, that's a protein. They also we have antibodies are part of that. Antibodies are protein structures that we just mentioned a little time ago that can recognize antigens or things that make us sick and can glue themselves to them. So that's kind of good. We have those in there. They're part of the immune system. And remember we talked about how when we get through capillaries, the blood is pushed out because the heart pumps it out. Hydrostatic pressure. But on the other side of the capillaries, how does the blood come back into the vessels? And that's the osmotic pull, that solute pull that brings water back in. And there's some proteins that don't leave the blood that then do that. And those proteins are basically called albumins. Those are the most numerous proteins we have.